Okay, so we're going to move on to, we're skipping 1.4, so 1.5 is the next section we're doing. It's 1.5. Oh, did you guys see my email about the first test? So that's February 13th, lucky number, is I'm scheduling the first test. So 1.5, we're going to look at exponential models. So in order to talk about that, I have to actually probably tell you what an exponential function is. So some of you might know this, but some of you might not. So it's a different kind of function than what we've described before. So we talked about what polynomials are, what radicals are, what rational functions are. But this is a new kind of function, has a very particular kind of behavior, and we're going to look at this function and how we can actually use it. So let's start with that definition. An exponential function is one of the form y equals a to the x, where we're usually going to be assuming that a is greater than 0. If it's a negative, we can factor it out, and we'll have to deal with that on a case-by-case basis. But a greater than 0 is a constant. And of course, it's clear that x is the independent variable here again. Y is a dependent variable. So, example, y equals 2 to the x is an example of an exponential function. Y equals 1/2 to the x is an example of an exponential function. Y equals pi to the x is an exponential function. Anything that has a base is a constant, the power is the variable x, you call that an exponential function. Also, non-example, which at this point it should be obvious, but I want it to be in the forefront of your mind to avoid future mistakes. You see, x squared is not an exponential function. Right, this is a polynomial. The main difference here is that the base here is the variable and the power is a constant, versus when the base is a constant, the power is a variable. They behave very differently. And this is important later on because I'm going to be giving you some rules when we actually get to calculus about how to differentiate functions. And some of it is going to be based on a power, and sometimes students apply the wrong rules to the wrong kinds of functions. So it's very important that you note differences like that, where the variable is in the function, where the constant is in the function, etc. Because it will make a big difference. Okay, and the exponential functions behave very different. They're a very different kind of function to a polynomial. So this is what's called an exponential function. There's some things to note about an exponential function. Is they have exponent in their name. So the first thing to realize is that they obey the laws of exponents. So normally when you're talking about laws of exponents, we write down the formulas to look something like this, where x is the base. So you have x to the a times x to the b is x to the a plus b. All those rules still apply when the base is the constant, the power is the variable. The rules still apply. So, for example, if you have two functions, a to the x, and you multiply by another function, a to the y, you do get a new function that's a to the x plus y, right? Or if you have a to the x divided by a to the y, you get another function that's a to the x minus y. You get a to the x raised to the y. That's a to the xy. Where these guys are both, x and y are both independent variables here. You can think of them as two functions, but all the rules still apply. What's a to the x over y?
A to the x minus y.
This one? This one here. In the power, you have x over y. Yeah?
Y root a x into the x.
Right, don't forget these rules. If you have a to the minus x, what is that? 1 over a to the x, right? Which, because there's a 1, you could also notice that that is 1 over a to the x. And so, for example, I can think of this function as such a function. I can think of this as being 2 to the minus x if I wanted to, right? Which will kind of tell you about the graphs of how something like that would look. And we'll get to that pretty soon. But I want you to be aware that the exponential rules apply. So if later on when we're working on more complicated functions and you have exponentials all over the place, you should know that you can simplify that function using laws of exponents. So they're not immutable to that. Other important things that you need to know about exponential functions is what their graphs look like. Graphs. This is the main generic exponential function. So here's where you have y equals a to the x. Your a is greater than 1. By the way, if you want to make your a less than 1, you just think of it as 1 over something that's bigger than 1, and then the rule would apply here. Okay. So in that case, and by the way, if it's equal to 1, you just get 1 to the x. It's just a straight line, so it's not an exponential function anyway. So, does anyone know what this looks like? Yeah?
It's never touching 0, so it's going to exponentially go into infinity on both sides with negative and positive.
On both sides? No. Does anyone know what it looks like? Can you draw it with your finger or? Yeah, well, it goes this way. Right? Remember, we're assuming our a is a positive number. So yes, it never will touch the 0. It's never 0. It approaches, as we say, asymptotically to the x-axis. So it always gets closer and closer and closer and closer, but it never actually touches the x-axis. It just gets smaller and smaller and smaller. But as your x value increases, it shoots up, right? And it can increase faster eventually than any other polynomial. That's one of the big differences. It doesn't matter if you're comparing something like 2 to the x compared to x to the 1 million power. It doesn't matter. Eventually, this guy is going to supersede it, right? That's why one of the reasons why exponentials, they're very different kind of functions. They grow very fast. Okay. So it'll like shoot up to infinity at a steeper rate than any polynomial can actually achieve over time. Okay, so those are just some differences. But that's what the main generic graph looks like. And of course, transformations apply. So all the old rules I told you we went over about transformations of functions, they still apply. So in the case where I have something like a to the minus x, or remember this I could think of as 1 over a to the x. When you make the x negative, what happens to the graph? Huh? What happens to the graph? Like, what's the rule? Tell me the general rule.
So the x-axis.
It flips in
X-axis.
the y-axis, right? So it's going to, you're going to take this picture and you're going to flip it there. So that one would look like this. What about if you have y equals minus a to the x?
It'll flip over the x.
So this one will flip over the x. So that would look like this. What about minus a to the minus x?
It's like the negative x1, but flip over the y, and over the x-axis.
So that would look like this. So you should realize that all the old rules apply to these functions. They behave differently, but they're not different in terms of their properties. They still will obey all the math rules that you're used to, the laws of exponents. They still also will behave under transformations in exactly the way that all other functions do. So if you make the x negative, it flips in the y-axis. If you make the outside of the function negative, the overall function negative, it flips in the x-axis, and so on and so on. So all of those things still apply. But this is the main behavior you're going to want to remember this function for. And remembering the pictures, it's actually important that you remember what these pictures look like, because later on we'll be doing computations where knowing the picture in your head helps you with the computations, and it helps you to kind of know what approach you want to take towards solving the problem. Okay, so when we get to limits, you'll realize that knowing the graphs of functions is actually going to be super important. I'm going to single someone out. There's one exponential function in particular that is very important to us as calculus students. When it comes to calculus, this particular exponential function is very important. Anyone guess what that is? Does anyone know? Experience with that? What function I'm thinking of? Yeah? E to the x. And like, wait, I thought the base was supposed to be a constant. E is a constant. Okay? So we're going to be using this guy all the time. This here is a number, right? It's a symbol that represents a number. It's E for Euler's number because it's named after the Swiss mathematician Euler, who lived in the 1700s, and he actually approximated this number to like 20-something decimal places without the use of a calculator or a supercomputer, which is very impressive, by the way. It's an irrational number. If you're wondering where it comes from, so E, by the way, is roughly going to be 2.718 millions. If you actually plug it into your calculator, you'll be able to find a value for it. But usually, you'll be able to leave your answers in terms of units. Okay, so that's roughly the value of it is. It's also, and at this point you won't know what I'm talking about, but pretty soon you'll know. It's the limit as n approaches infinity. We'll talk about what limits are later. 1 plus 1 over n to the n. This is kind of where this number came from, where it popped up, right? And if you don't really recognize where that came from, I'll give you some context for that expression here. This guy here. Take the compound interest formula. Plug in time equals 1 year, and plug in the interest rate equals 100% interest rate. Like you really want to loan someone money and really screw them over. You say, I'm going to charge you 100% interest rate. And you're compounding it, n is the number of times it's compounded. Compound interest is a very important idea. And so a lot of things grow with compound interest, like credit card debt and things like that. So it's an important formula to know, but this is one particular instance of that formula. It's a very theoretical kind of number. So basically, if you say you're applying a loan for 1 year at 100% interest rate, where n is the number of times you're applying this interest, right? So the number n can vary. You can say, I'm going to charge interest just at the end of the year, so it's kind of end up being simple interest, or twice a year, so after every 6 months I'll charge you interest, or you can put 3 times per year, 4 times per year, 5 times per year. What if you get really greedy and you're like, you know what? Any number that you put here, I'll charge you more than that number, right? Not every day, every second of every day, every half second of every day, every quarter, every 1 million, the smallest infinitesimal fraction of time that you can imagine, I will charge you interest that often on this loan. That's what n goes to infinity means, where the number of times I'm applying this interest is getting huge in 1 year. And you might think that that would mean at the end of the day, you'll have an infinite amount of money, but that's actually not true. You'll end up with that much times your money. So if someone loaned you $1 and under these conditions gave you that loan, at the end of 1 year, you would owe them $2.72. Right? So it's a very interesting number. So it came out of that idea, like, you know, when someone's in banking and finance and they're just looking at theoretical models of how interest works. This guy popped up, right? And it turns out that this, for some reason, you'll realize in various instances in calculus, this expression actually just pops up out of nowhere. You'll be trying to work out a formula for something, and boom, that shows up, and you're like, whoa, right? So in calculus, it's actually it's a very important number, and a lot of calculations become easier in terms of that. And there will be times when we can start with another exponential function, but we kind of rewrite it to have this base, because it's that convenient for calculus. It's a very important function, and e itself is a very important number. And I do want to emphasize that e is a constant. E is a constant. We'll see later why I have to emphasize that. E to the x, though, is a function. Right? Don't forget that it's the x that makes it well, constants are, we can think of as constant functions, but you know when I mean a constant one. Okay. But e to the x, this guy will behave like an exponential function, while this guy, if you were to graph him, he's a horizontal line, right? And that's an important distinction. Right? When we get to derivatives, you'll realize why that's an important distinction. So e on its own is just a number, it's a constant, it's around 2.7. But if you take it raised to the x, you get a very important kind of exponential function. In fact, we give it a very conceited name. It's called the natural exponential. It's the natural thing to use for calculus, if you're talking about exponentials. It's a very important guy. And there are many textbooks in which they will talk about exponential functions in general, and then they will dedicate an entire chapter just talking about this exponential function in particular. Right? So it's very important. Right? And we'll be doing a lot with it, so you'll get used to it eventually. But I want you to know that's out there. Another important fact. Now, there's no way I can show you all of the applications of exponential functions in this class, but be aware that they have many. Like, you're more likely in a real-world situation to use an exponential function to describe a situation than you are to use a linear function or many other kinds of functions. They show up all the time, all over the place. Many things in life grow, as we say, exponentially. Okay? Many things in life have a kind of inherent interest in them. So you'll see applications of this all over the place. You look at something like population dynamics. If you're studying a population, whether of people, bacteria, rabbits, whatever, somewhere there's an exponential function that's going to pop up in that study. You can study economics and finance, surely, right? This guy was invented by people really looking at compound interest, right? So economics, finance, financial models, right? It's all going to be in there. If you're looking at something like radiation, analysis or something like that. So if you're studying the radiation levels of Chernobyl, at some point you're going to be using an exponential function to describe how it's decreasing over time, right? You're going to, in various parts in engineering, right? So if you go for an engineering degree, you will eventually do a math class where you're going to do a lot of applications that have to do with engineering, and things like things that tend to oscillate or vibrate. So let's say you're designing an engine, you're designing a piston, you're having a spring system to absorb shock. At some point when the mathematics is behind that and when you're working on it, there's going to be an exponential function somewhere in there, right? It's all over the place. It's very ubiquitous, many more. Right? And there are a few applications that we will be doing. For example, we will look at things like population and radiation. And we'll look at some things in finance when we're compounding money, but just understand that these guys have tons and tons of applications. But because we're not going to look at all of them, I want to really zoom in on the kinds of applications we will care about. And so I want to give you guys just a criteria for judging when an exponential function might be useful for you to use in this class. So last time we talked about linear models, and I gave you two main reasons you would know that you need to use a linear model. One, I will specifically mention the word linear in the problem, or you'll notice that there's a quantity that you're measuring that's changing by a fixed value over time, right? So in the case of the car rental company, where I said, for every mile you drive, they charge you $2 more. It's always going to be $2. The amount that they're charging you per unit mile is always the same, right? So that's how you know you need a linear model. Exponential model is kind of a similar characterization, but it is different in one important way, right? So for one, it also applies that you're specifically told to do so. There will be problems where I'll say, use an exponential model, or this grows exponentially, or this decreases exponentially. So I will mention the word exponential in it. So you'll see a phrase like the word exponential, or exponential. You might also see phrases like proportional to its current size. Right? So you see phrases like this, it means you need to be using an exponential. 2. And this is kind of picking back on this last statement here. You know you need to use, let's say I don't mention a phrase like this. How do you know you need to use an exponential function? Doesn't have to go, could actually decrease. Let's say that changes. By a fixed relative amount. So it's linear if it changes by a fixed absolute amount. This changes by a fixed relative amount. And by relative, I mean by a percentage of its current size. So what would that look like? So let's say in that car rental example, and this shouldn't be in any rental agreement, but let's say someone charges you this way. They didn't say we'll charge you $2 for every mile, but they say we will charge you the dollar value of 2% of the miles that you drive. Right, so now you're not talking about a fixed value, you're talking about a relative value. The more miles you drive, the larger that chunk of money is going to be. Even though it's a fixed 2%, right? That means if you drove 50 miles, they'll charge you $1, right? If you drove 100 miles, they now charge you $2, and so on and so forth, right? So it's not they're always charging you a fixed amount. They're charging you based on a fixed percentage, right? So they say, okay, I'll charge you 2% of whatever the current size is. That yields an exponential model. That's a relative growth rate, right? It's still fixed, but it's a fixed percentage, not a fixed value. Okay? And whenever that's happening, you say you have an exponential model, right? So if you actually plot a function to track that, it would look like an exponential function and not like a straight line. Now, that's all I want to tell you guys. We'll do a lot of more word problems in a later section, but I think that's enough for you to be able to do the homework required. In this section at least. Because we'll be coming back to these kinds of functions ever so often. So that ends that section. 1-on-1.
How long is the chapter? Or like just that?
I mean,
That's weird though.
we could start this, but I don't think I'll get far enough in 10 minutes to stop it. It doesn't make sense to stop. I think we'll just end class. It's like, to introduce this topic, there are like 10 rules I need to give you. There's no way I'm going to get through like 2 of them, so I'm going to like leave you like, what's the other 8? So we'll stop there. So 1.5 is due for next class. You should also note that I do have office hours today. I'll be in room 410 in this building. About what time? 1 to 3:30 or something?